Okay, hi, my name is Suzanne Tank. I'm an assistant professor at the University of Alberta, and tonight I'd like to talk to you about the power of rivers. So at this point in the evening, it's not going to come as any surprise if I start off by saying that freshwater systems are our lifeblood. Rivers in particular function as the pulsing vein of continents. They provide us with transportation, for better or for worse with power, and perhaps most critically from the human perspective, with food to eat and water to drink. Tonight, however, I'd like to talk about another type of power that rivers possess, and that's their ability to help us understand the landscapes that surround them. Tonight, I'm going to talk to you about rivers as integrators and bellwethers of change. So one of the fundamental characteristics of rivers is that they collect water from the landscapes that surround them. As water falling on land flows downslope to freshwater systems, it carries with it the chemical signature of the land over which it has traveled. As a result, you might imagine that you could stand at the outflow of a major river, take a sample of that water, and use its chemical signature to tell you about the composition and functioning of its watershed, the land that surrounds it. You could do this repeatedly over time and also then understand how that watershed was changing. And then you could pivot to face the coastal ocean and use the information contained within that chemical signature to also tell you something about that ecosystem and how it was functioning and how it was changing over time. We see this characteristic in the Mississippi River, where farming in the upper reaches of that catchment, shown here in green, is causing a continued increase in nutrients in its outflow to the Gulf of Mexico, and a dead zone in that coastal region that has impacted fish and fisheries in this ecosystem for decades. We see this characteristic play out in a bit more basic way throughout the world's river mouths, illustrated here at the bottom for the Amazon, where the simple outflow of fresh water into a saline environment causes ocean acidification hotspots, which you can see here in red, which overlay themselves on the global phenomenon of ocean acidification that's caused by rising carbon dioxide concentrations. Today, however, I'm going to tell you a story about the Arctic and how large rivers can help us understand Arctic change. So one thing that alarms pretty much anyone who's spent very much time thinking about climate change in the north is the fact that permafrost, or perennially frozen soils, and I'm showing the world's permafrost soil extent here in purple, contain twice as much carbon in the organic form as there currently is carbon dioxide in the atmosphere. And this permafrost, of course, is thawing. And whether this permafrost thaw plays out as kind of a gradual landscape collapse and wettening, which I'm showing in the top left, or kind of catastrophic landslides and land collapses that move thousands of cubic meters of sediment, the net result is that permafrost thaw exposes previously frozen soils to biological and chemical processing and allows the chemical constituents locked up in permafrost, including carbon, to become part of a vast flowing freshwater continuum that connects land to freshwater to the sea. So the question then becomes, is this change on land having an effect on freshwater systems? And if it is, what can this tell us about change writ large in the Arctic? To answer this question, I, with colleagues, spent some time analyzing a 40-year data set that exists for the Mackenzie River, and I'm showing the Mackenzie catchment here. So the Mackenzie, for those of you who aren't familiar with it, is a huge system. It covers 20% of the Canadian landmass. It has its headwaters in Jasper. Its southern boundary is about 100 kilometers north of Edmonton, and it eventually flows to exit to the Beaufort Sea in the Arctic Ocean. The watershed ranges from being completely underlain by permafrost in the north to being underlain by discontinuous permafrost in the midsection to having permafrost entirely absent in the south. And this is also a catchment with a fair bit of soil carbon contained with it, shown by kind of the darker splotches on this map on the right. So what we were looking for is an understanding of how the flux or total mass of organic carbon up at the mouth of this large river was changing over time. Our data set started back in 1978 when there were 98 gigamoles, or about 1 billion kilograms, of organic carbon in the dissolved form leaving the Mackenzie River each year. When we looked forward over time, however, we saw this value consistently and significantly increase, and in fact increasing by a fairly astonishing 40% over the last 40 years. This increase is significant because we know that the organic carbon we see in freshwater systems is not stable in this state. This is a primary food source for bacteria who metabolize it to produce carbon dioxide. So this organic carbon that we see at the Mackenzie mouth represents a signal of carbon dioxide production that has already happened further upstream. And we also know, based on past studies, that most of what remains at the mouth of major rivers, this trend that we see here, will be broken down to carbon dioxide in the Arctic Ocean. So this trend is clear and striking, but the question remains, why is it occurring? One hint about cause comes when we look at trends in the tributaries or subcatchments within the Mackenzie system, for which we also have these long decadal set data sets. When we do this, we see clear and similar increases for all the tributary sites that have significant permafrost within their catchment. I'm not showing the graphs with the trends here, but this is signified by the golden upwards arrows on this map. But no change whatsoever, no trend in the south in subcatchments where permafrost is absent. And this is signified here by sites with the green dots and green sidebars. So this suggests really strongly that we're seeing a riverine signal of permafrost thaw playing out over time in the Mackenzie system. And of course, this change can be expected to affect the ecology of this river system itself. So for example, by increasing bacteria relative to algae and thus fundamentally changing the food web structure within this aquatic ecosystem. We can also expect a significant effect on the nearshore ocean, and in a fairly wide-ranging way. So this here is the Mackenzie River plume, and you can see, as you see from space, and you can see that the impact of this river water carries a fair distance offshore. So one example of the effect of this change in the coastal ocean is that bacterial decomposition of this increasing organic carbon that's delivered to this environment can be expected to increase carbon dioxide concentrations in the coastal ocean, which will in turn decrease pH, and then act as another additional factor to increase ocean acidification and overlie on these other factors that I've already talked about. So clearly, our north is changing. Over vast spatial scales, change on land is integrated in the chemical signature of the water that drains landscapes. This change fundamentally affects how freshwater systems function. As a result, our rivers are both powerful, but they're also at the same time vulnerable. They're sentinels of change while at the same time being fundamentally affected by the change they can be used to detect. And as other speakers have said, we are increasingly coming to understand that this change is often occurring rapidly and that it can also be very substantial. Thank you.